Hello friends, here in this video we will see the stresses in helical spring. Okay, a round wire helical compression spring is subjected to an axial force F, right? Okay, we have two figure A and figure B. Figure A is axially loaded helical spring. Suppose F is equally axially loaded. Okay, and figure B, it is the free body diagram. Okay, now what is capital F, what is capital D, what is small c, what is D, what is N, right? So F is equal to axially force on the spring in terms of Newton. Okay, so F is equal to axially loaded, right? Capital D, it means the mean coil diameter in terms of mm, right? Here, okay. Small d means wire diameter, it is wire diameter small d. Okay, and n is equal to number of active coils. Okay, okay, you can see both the figure A and figure B, it is the helical compression spring, right? Okay, the effect of an axially force, the effect of an axially force F is equivalent to two types. Okay, two types effect. The first one is torsion moment. Okay, torsion moment T, capital T is equal to F into D by 2 acting on the wire cross section. F into D by 2 acting on the wire cross section. Okay, we already see in the figure. Okay, here F into D by 2 means force into perpendicular distance. Okay, here is the force F and it is total is D and half of the D is D by 2 means force into perpendicular distance, right? So that's why T is equal to F into D by 2 acting on the wire cross section. And second one is direct shear force. Direct shear force. Okay, and it is called F acting on the wire cross section, right? Hence the stresses induced in the spring wire. Okay, the stresses induced in the spring wire. First one is torsion shear stress. Okay, it is denoted by tau T. And second one is direct shear stress. It is denoted by tau D. Okay, tau T and tau D. Okay, now first we can see torsion shear stress. Okay, torsion shear stress induced in the spring wire due to the torsion moment. Okay, torsion shear stress induced, okay, due to the torsion moment. Okay, we can find out. We have the figure, we have the equation of torsion, right? So torsion equation is this one. T by J is equal to tau upon R is equal to G theta by L. It is the torsion equation. Okay, but we want only T by J and tau upon R. We do not require G theta by L. Okay, so we can it cancel out. G theta by L is cancel out. Okay, okay, now T by J and tau upon R. T by J is equal to tau upon R. So the value of, we have value of T is equal to F into D by 2. Okay, okay, J means polar moment of inertia for the cross section wire, circular cross section wire. Okay, and it is pi by 32 D raised to 4 and R is equal to D by 2, small d by 2. Okay, radius of wire. Okay, so we have all the values T, J and R. Okay, all the values are put in this equation. T by J is equal to 2 upon R. So we get tau D after calculating. Tau D is equal to 8FD by pi D cube. Okay, this one is the torsion shear stress equation, right? And the simple diagram of the torsion shear stress is like this. Okay, Okay, next one is direct shear stress. Okay, direct shear stress induced in the spring wire due to the direct shear force. Okay, and direct shear force is F, and it is given by, so the simple torsion equation is tau is equal to force upon area for the direct shear stress. So the equation is tau d is equal to F by A, and A is equal to pi by 4 d square. Okay, it is the circular wire area. Okay, so that's why tau d is equal to, after calculating, equation is tau d is equal to 4F by pi d square, and the figure is for direct shear stress is like this. Okay, for direct shear stress. Okay, now resultant shear stress. Okay, the summation of torsion shear stress and direct shear stress is equal to resultant shear stress. Okay, now hence the maximum resultant shear stress in the spring wire is given by tau is equal to tau t plus tau d. That means torsion shear stress plus direct shear stress. Okay, and it is equation number 3. Now substituting equation 1 and equation 2 in equation number 3, right? So equation 1 and equation 2, that means first one is equation is this one. Okay, and the second equation is tau d. These both equations are put in the equation number 3, right? So tau is equal to 8fd by pi d cube plus 4f by pi d square, right? After calculating, the equation is 8fd by pi d cube, it is common out in this equation. Okay, now the remain is 1 plus d by 2d, right? It is the calculation. Now tau is equal to 8fd by pi d cube in bracket, under bracket, 1 plus 0.5 by c, otherwise 1 plus 1 by 2c, both are same, 1 by 2c. Okay, because of the d by d means capital D by small d is equal to c, spring index. Okay, mean coil diameter by wire diameter. Okay, now tau is equal to Ks into 8fd by pi d cube. That means Ks is equal to 1 plus 0.5 by c. Okay, and what is this we can see later. Okay, so the final equation of the resultant shear stress is tau is equal to Ks into 8fc by pi d square. 8fc because of the capital D by small d is equal to c. Okay, so the resultant shear stress equation is this one, right? Where Ks is equal to what? Ks is equal to shear stress concentration factor, sorry, shear stress correction factor, right? And it is equal to 1 plus 0.5 by C or 1 plus 1 by 2C. Okay, both are same. Okay, we can see the shear stress correction factor Ks. What is this? So the shear stress correction factor is used to account for direct shear stress. Okay, account to direct shear stress. Okay, in addition to the torsion shear stress. Okay, whenever direct shear stress is induced, then we can use the shear stress correction factor Ks. Okay, so it is given by Ks is equal to 1 plus 0.5 by C or 1 plus 1 by 2C. Both are same, right? Okay. Okay, you can see the different types of stresses induced on the wire. Okay, the first one is torsion shear stress. Okay, figure we already see. Second one is direct shear stress, we already see in this figure. Okay, now third one is combined torsion and direct shear stress. Okay, like this figure. And the last one is combined torsional, direct and curvature effect shear stress, tau. So this type of figure is this, right? So this one is the stresses in the spring wire, right? Okay, next, resultant shear stress with curvature effect. Okay, first one is, okay, second one is resultant shear stress with curvature effect. Now curvature of the wire is increase. Okay, curvature of the wire is increase the shear stress on the inner surface. The curvature of the wire is increase the shear stress on the inner surface of the spring and decrease it slightly on the outer surface. Okay, okay, listen carefully. Curvature of the wire, okay, then increase the shear stress on the inner surface. Inner surface is increased shear stress, okay, and outer side is decrease. Clear? Okay, in order to consider the effect of both, in order to consider the effect of both direct shear stress as well as curvature effect stress in addition to the torsion shear stress. Okay, so the shear stress correction factor Ks is replaced by another factor Kw, is known as wall factor or wall shear stress factor. Okay, okay, whenever curvature effect is addition in place of the direct shear stress. Suppose direct shear stress you can use Ks, but in case of the curvature effect is occur on the spring, now at that time you can use Kw, wall shear stress factor. Okay, okay, now we can see what is wall shear stress factor. Okay, all walls factor, and it is denoted by Kw, walls factor or walls shear stress factor. Okay, okay, wall shear stress factor is used to consider the effect of direct shear stress as well as curvature effect stress. Okay, in addition to the torsion shear stress. Okay, and it is given by, remember this, Kw is equal to 4c minus 1 by 4c minus 4 plus 0.615 by c. Okay, it is the equation of Kw, wall shear stress factor. Okay, and it is, remember, okay, you can memorize this. Okay, hence the maximum shear stress induced in the spring wire which is at the inner surface. So it is given by tau is equal to Kw under bracket 8Fd by pi dq. Now Kw, okay, it is the, in the direct shear stress we can use Ks, and the curvature effect we can use the Kw, right? Okay, and tau is equal to Kw into 8Fc by pi d square, because of the d by d is equal to c, we already see that. Okay, now the shear concentration factor due to the curvature effect is localized and is significant only when the fatigue load is present. Okay, okay, remember, now static load is present, you can use Ks, means shear stress factor, and fatigue load is present, then you can use the Kw. Okay, okay, I repeat, shear stress correction factor due to the curvature effect is localized and significant only when the fatigue load is present. For static loading, this stress can be neglected. Okay, for the static loading, the fatigue load means Kw is neglected. Okay, because it will be relieved by the load. Okay, it will be released by the local yielding with the first application of the load, right? Hence, the wall shear stress factor Kw is used when only in case of fatigue loading. Okay. Remember this sentence. Wall shear stress factor Kw is used when only in case of the fatigue loading. Okay. In case of the static loading, okay, the shear stress correction factor Ks is used instead of wall shear stress factor Kw. Okay, remember those two sentences. When fatigue loading is present, then wall shear stress factor is used, and static loading is present, then Ks means shear stress factor is used. Clear? Okay. Thank you. This one is the stresses induced in the helical compression spring, right?